Hello there. So we left off last time talking about Milankovitch cycles. Go back and look at that if you'd like. But now we're going to talk a little bit more about how we establish the temperature history of the Earth. And you've seen these graphs before. So on the left is a graph of mostly reconstructed temperature. So various traces here. I mean, you can sometimes see these graphs all sort of averaged together. But so often you see this data all smoothed and averaged together because, as you can see, it's pretty noisy. And this is from various models of taking a lot of different proxy data. Remember, we talked about proxies briefly before, and combining it. And the reason we need proxy data, again, something we've talked about before, but remember that the reason we need proxy data is that we don't really have modern thermometers, things that we can actually trust to make accurate temperature measurements prior to about 1880, late 19th century. And so you might think, oh well, 100+ years of temperature data, that's a pretty good baseline that we can use to establish the fact that our temperatures are going up and we're hotter than we ever have been before in human history, that kind of thing. And that would be true, except if you start thinking about the Earth rather than humankind. And if you think about the Earth, the geological history of the Earth and the climate history of the Earth is colossally long on the human timescale, right? We live at best 100 years, but the Earth has been around for billions. And even if you limit it to sort of the more modern era where, the Earth had settled down a little bit and there wasn't quite so much volcanic activity and there were actual little creatures running around on the surface of the Earth, all of that kind of stuff, you're still talking about millions and millions of years at the very least. And so to establish a more consistent baseline, scientists have put a lot of time into trying to extend our temperature record prior to when we had thermometers in the late 19th century. And you can see that this graph goes all the way back to about 1000 AD, or I guess the more modern thing, 1000 CE, current era. And so we're looking here at a little over 1,000 years of temperature data. And you note that as soon as we get out of the modern era, so this being about the cutoff for the modern era right there, and everything before this gets noisier. So there's less certainty in the data. And yet, if you get enough data from enough different sources, you can start drawing some really strong conclusions about what the temperature was doing in Earth's history. And once you understand what it was doing, it's a lot easier to attack questions like, well, why is our climate doing what we're doing? And of course, gives us a much stronger comparator when we're talking about today's temperatures and how they are exceptional or not in the recent temperature history of the Earth. So let's look at a couple of proxy data sets. I gave you a reading on ice cores that I hope you've done. If you haven't done it, please go to the Brightspace page, look it up. I think it's in week 11, it just says information on ice core proxies, I believe. But I'll talk about two different ones here. And one is pretty famous. If you've read much about climate science at all, you've probably heard about tree rings as proxies. And the other one, so there's the tree rings. And the other one we're going to talk about are sediment cores and sort of the contents of the sediment, how we get temperature of the ancient Earth via those things, okay? So first, over here on the left, if you concentrate your efforts right over here, we're looking at the tree rings. So everybody's familiar with the idea of tree rings, right? So this is a cross-section of a tree. You have its first year growth here right in the middle. And then each ring thereafter, assuming that we're talking about a species of tree and a part of the Earth in which there's just one growing season, each ring thereafter represents a year in that tree's growth. So after 1 year, 2 year, 3 year, 4 year, 5 year, and you can count up on and on and on and on. And trees can live hundreds or even thousands of years for certain species of trees. And so this gives us a pretty long temperature history of the Earth if we can correlate tree rings accurately with temperature. And the problem that we sometimes run into, or we always run into with the tree ring proxy, is that there are a variety of so-called confounding factors. Okay? So, for example, precipitation and temperature, both of those things can affect the ring width in trees, and they'll affect that ring width different amounts depending on whether there was too little rain or way too much rain combined with high temperatures or low temperatures, and the species of the tree matters, and also where the tree is in terms of elevation, in terms of its proximity to groundwater, things of that sort. Okay? So there's a lot of so-called confounding factors. However, they can actually be worked around. For instance, one of the ways they often do it is to pick out species of trees about which we know a lot of the biology. So we know what factors affect their growth in different ways. And then we select trees, usually many trees, to take data from that are, for instance, along the tree line, right? So if you look at a bunch of tall mountains, typically there's a tree line where the trees stop occurring because of reduced temperatures and things like that you get at higher elevations. And that tree line represents sort of the what's the term? The limiting stand of the tree. And in those conditions, there's a lot known about whether temperature or whether precipitation is the thing that drives growth the most in those kinds of trees. There's a lot of studies going around and around and around trying to ferret out how these factors are all related to one another and trying to devise experiments to tease out these temperature bits of data from all of the other factors that can affect tree ring growth. Okay? And a great deal of progress has been made, and so tree rings have become a reasonably reliable proxy for historical temperature data on the Earth when the experiments are done properly. Now, it goes without saying, I should say this, that we're not chopping down a bunch of trees every time we do a tree ring proxy study. What we're doing is we're taking a core, so they take a special tool that essentially like a hand drill, and they carefully drive it into the tree and pull out a very long column, narrow column from the very center of the tree. Well, if they want a really deep core anyway, if they want to look at the very first years of the tree's growth. But a core that runs all the way into the tree. And then they look at the rings on that core rather than having to chop down the whole tree, and typically it's done so that the trees will survive after having their cores taken. Now, in addition to that, a lot of trees are cored. So you're not just going out there doing one core saying, sweet, we're done. A whole lot more statistically needs to be done to tease out these confounding factors and to make sure that when you're talking about, the 20th tree ring, that when you're looking at another core of another tree, that the 20th tree ring is also referring to the same year. That's a tricky thing to do, and to do it, you need a lot of cores from a lot of trees. Now, modern rings can be correlated with modern temperature data, right? So sure, if you have a 1,000-year-old tree, the first 900 years of it, we can't look at modern temperature data from that part of the Earth and try to draw conclusions about the effect of temperature on the growth of that tree. But you can look at the most recent 100 years or 50 years or whatever you have a temperature record for with thermometers, and you can establish the validity of your conclusions about certain tree rings and how much they correlate with temperature by comparing it to the temperature of the modern era. Lastly, and this is kind of interesting, though it's not the primary way that these are used, you can also look at the isotopes, carbon, oxygen, hydrogen, within the hydrocarbons that make up core wood samples. And through isotopic analysis, you can actually tease out temperature data as well. So the tree ring cores are a valuable source of data, both just based on analysis of the structure and thickness of the rings, but also of the isotopes that are in there, and that, as we will see for one case, it can be correlated with temperature quite strongly. Now, the other one that I'll touch on here before we wind up this video is the sediment cores. And sediment cores are a similar idea. If you go to the ocean floor, typically, some aquatic environment, and you take a core there, so you drill down, you have layers and layers and layers and layers and layers and layers of sediment, and you can correlate that with age. And in all of those sediments are the shells of two sort of big families of tiny, tiny, tiny little organisms. So millions of these tiny guys, diatoms on the left and forams on the right. When they die, their shells fall down into the sediment and they get all compacted together. And so when you pull out these sediment cores, you can look at the shells of these guys. And as it turns out, as they grow their shells, they incorporate oxygen. So in the case of diatoms, you're talking about silicon dioxide. So 2 oxygens and silicon primarily. And with the forams, these guys over there, they have primarily calcium carbonate shells. Okay, but both of them have a whole lot of oxygen in them, and they incorporate that oxygen, and we have a couple of common isotopes of oxygen that change in their proportion within these shells dependent on what the temperature was like in the environment of these diatoms and forams when they died. And next video, we'll talk a little bit about the so-called oxygen cycle here on Earth and the relative proportion of these isotopes and how that correlates with temperature. So I will see you then.